Greetings. In this work, we will study some geometrical and topological properties of fractal networks or fractal graphs. This work is done in collaboration. Fractals are complex and fascinating geometric structures characterized by their ability to repeat a basic pattern at different scales. This phenomenon, known as self-similarity, means that the smaller parts of a fractal are smaller scale replicas of the whole. Fractals are found in both nature and mathematics, and their study spans disciplines ranging from physics and biology to art and computer science. Fractals are not only objects of theoretical study, they also have practical applications in a variety of areas. In nature, fractals describe the structure of mountains, coastlines, clouds, and river systems. In technology, fractals are used in image compression, the generation of computer graphics, and the modeling of complex phenomena. In this work, we study the properties of graphs with some of these structures. In particular, we will study fractal graphs associated with the Sierpinski carpet, the Sierpinski triangle, and the Koch snowflake. The construction form of these fractals is usually known. However, when considering graphs with these structures, we usually consider displacements instead of subdivision. For example, for the Sierpinski carpet, step 0 is a square of side 1. For step 1, we move a copy of the previous step as shown in the picture. Note that we are not moving anything to the square that is right in the middle. For step 2, we perform the same procedure, but now displacing copies of step 1 and so on. Formally speaking, the instructions are shown on the screen. The Sierpinski triangle is constructed in a similar way. The Koch snowflake is constructed differently. In step 0, we have a C3 cycle. For step 1, we first replace each edge from the previous step with a path of 3 edges, and then replace each central edge with a C3 cycle. In the next step, we replace each edge in the previous step by a path of 3 edges, then we replace each central edge of the contour by a C3 cycle, and we do this again for each iteration. Now we will study a geometrical property about these graphs. Gromov hyperbolicity, introduced by mathematician Mikhail Gromov in the 1980s, extends the classical idea of hyperbolic spaces to a broad class of metric spaces and groups. Hyperbolicity in Gromov's sense is a simple concept, but at the same time it leads to a very rich general theory. This concept captures the qualities of negatively curved spaces like the classical hyperbolic space, Riemannian manifolds of negative sectional curvature, and discrete spaces like trees and Cayley graphs of many finitely generated groups. Hyperbolicity is a very useful tool that helps us in understanding the relationships between graphs and manifolds. There are several definitions of Gromov hyperbolicity which are equivalent. We will work with the definition of Gromov hyperbolicity given by the Rips condition for its geometric meaning. We consider a geodesic metric space X. In this space, we consider a geodesic triangle. We say that the triangle is delta hyperbolic if any side is contained in the union of the delta neighborhoods of the other two sides. We say that the space X is hyperbolic if there exists a delta which is valid for every geodesic triangle in X. As examples of hyperbolic spaces, we have that any tree is zero hyperbolic, since no matter where we choose the vertices of the triangle, we have that two sides contain the third one. Rn is hyperbolic only for n-por 1. Among other examples, among the applications of Gromov's hyperbolicity are the application to the routing model of the Internet, the security of information transmission through networks, and even the study of DNA. In addition, it has been shown that there is a relationship between several surfaces with negative curvature and very simple graphs. Moreover, from previous work we know that it is sufficient to consider simple and connected graphs, which in this case they all are. We will consider edges of length 1. The triangles have as their vertices the vertices of the graph or the midpoints of the edges. Finally, we have that the hyperbolicity constant is bounded by the diameter of the graph. For the aforementioned families of graphs, we obtain the following results. In the case of the Sierpinski carpet, for step n, we have that its hyperbolicity constant is 3 to the power of n. In this case, it coincides with the previously mentioned bound, half the diameter of the graph. In this case, the geodesic triangle has its vertices at 3 of the outer corners. In the case of the Sierpinski triangle, we have that for n equal to 0, the constant is equal to 3/4. For n equal to 1, delta is equal to 5/4. Finally, for n greater than 1, we have that delta is given by the expression we see on the screen. For the case of the Koch snowflake, we have for n equal to 0, delta is 3/4, and for n greater than 0, delta is 5/6 of 3 to the power of n. A single number representing a chemical structure in graph theoretical terms via the molecular graph is called a topological index if it correlates with a molecular property. Topological indices are parameters associated with chemical compounds that associate the chemical structure with several physical, chemical, or biological properties. These indices play an important role in mathematical chemistry, especially regarding quantitative structure-activity relationship and the quantitative structure-property relationship. Topological indices on graphs can be defined on vertices, edges, or some other parameter. In this work, the indices we consider are defined on edges. In particular, they work with the degrees of the vertices of these edges. In 1975, Milan Randic introduced a topological index, which has been used to predict various physicochemical properties of alkanes, such as boiling point, surface areas, and others. Later, this index was generalized to obtain the generalized Randic index, whose expression is shown on the screen. Note that if alpha is equal to -1/2, we have the classical Randic index. If alpha is equal to 1, we have the second Zagreb index. Another index of great importance is the ABC index. In this work, we consider its generalized form, given by the formula shown on the screen. Given a graph G, an irregularity measure is a numerical descriptor that is 0 if and only if the graph G is regular. In this work, we consider the following two irregularity indices. Considering these indices on the family of Sierpinski carpet graphs in step n, we obtain the following formulae. For the Sierpinski triangle, we obtain the following formulas for the mentioned topological indices. Finally, for the Koch snowflake, we obtain the following formulas. As mentioned before, topological indices have been used to study physicochemical properties of compounds to which a graph is associated. In this work, we decided to use the aforementioned indices to study a geometrical property of these families of graphs. In this case, the Gromov hyperbolicity constant. Consider the Sierpinski carpet graph. Given n, we have its hyperbolicity constant. Consider now a topological index, for example the generalized ABC. It is possible to find a value for alpha that approximates this index to the hyperbolicity constant of the graph. If we do this for various values of n, we can observe that the values of alpha have a behavior which seems to fit a linear model. In this case, for the generalized ABC index, we propose a fit for alpha as a function of n given by the formula we observe. Similarly, we have similar fits for the alpha values taking into account the two regularity indices and the generalized Randic index. Finally, we consider similar fits for the Sierpinski triangle graphs and the Koch snowflake. In this picture, the first row corresponds to the analysis for the Sierpinski carpet graphs, the second row is for the Sierpinski triangle, and the third row is for the analysis of the Koch snowflake graphs. The first column shows the behavior of the indices and the hyperbolicity constant for the first 15 values of n, while the second column takes the first 100 values of n into account. The third column shows the behavior of the relative error of each index with respect to delta. That would be all. Thank you very much for your attention.